So if you haven't signed in, then sign in on the link. Alright, so I'm going to be going over some crypto stuff. This is part 1. Part 2 is going to be next week, because this is the first one that actually takes 2 weeks, I guess. But first, we have a CTF up. It's at ctf.utdcsg.me, in case you didn't see the announcement on the Discord. So you can go ahead and do some challenges. They should hopefully be fun. At least I think they should be. Alright, so the first thing that we're going to go over is just basic encoding. So basically, like, how are numbers actually encoded, and then what are some other ways we can encode information. So numbers have what's called a numerical base. It's basically every time you see a number, it's basically a sum of multiples of that base. So you'd have like some number times the base to the 0th power plus some number times base to the 1st, and so on. And that some number will go from 0 to 1 less than the base, because otherwise then you'd add 1 to the next one. The one that everyone's probably the most familiar with is base 10 or decimal. The digits obviously go from 0 to 9. And for example, the number 123 is just 1 times 10 to the 2nd plus 2 times 10 to the 1st plus 3 times 10 to the 0th, which is 100 plus 20 plus 3. And then the natural, I guess, base for computers is base 2 or binary, and you'll often see them either with a 0B prefix in front, or more commonly it's just groups of 4 or 8 zeros and ones. So the digits go from 0 to 1, and for example 1110 in binary means 1 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 1st plus 0 times 2 to the 0, which is just 8 plus 4 plus 2, or 14. In these slides, I guess, if I'm going to have binary, I'm going to put the 0B prefix in front just to make it more clear. And another commonly used base, especially with computer stuff, is base 16 or hexadecimal. It has the digits 0 through 9 and A through F. A through F being representations of 10, 11, 12 through 15. These are generally either a 0x prefix, or they're just going to be in groups of a power of 2, so it'll be like 2 digits or 4 digits or 8 digits. Generally not more than that unless it's just a stream of hex. And for example, 0x 1, 2, 3 and would be 1 times 16 to the 2nd plus 2 times 16 to the 1st plus 3 times 16 to the 0, which is just 256 plus 32 plus 3, which is 291. And then binary and hexadecimal, it's very easy to convert between them because base 16 is just the same as base 2 to the power of 4. So the 0 through 15 for the hexadecimal digits is the same as binary 0000 to binary 1111, which means that each group of 4 bits represents one single hex digit. So 0x42 would be in binary 01000010, and that's 66 in decimal. Another base that's used is base 8 or octal. It's not used as much anymore. It was a lot more common when you didn't have like a nice even like bits for the word length on, so you had like 36-bit memory or something like that. And these are going to be have a 0 prefix, or it'll be in groups of 3. And the digits for octal are 0 through 7. So 0, 1, 2, 3 would be 1 times 8 to the second plus 2 times 8 to the first plus 3 times 8 to the 0, which is just 64 plus 16 plus 3, or 83 in decimal. 8 is also a power of 2, so base 8 is just base 2 to the third, which means the 0 through 7 from octal is just the same as binary 000 through binary 111, where in this case each group of 3 bits is 1 octal digit. And if you have any other power of 2 base, it'll work similarly, but there's not going to be a lot more that you're going to be seeing anywhere, because then eventually you start running out of characters and then things get more interesting. But basically 042 would be in binary 100010, which is 34 in decimal. Then ASCII is just a way to represent like normal text but in numeric form. Each character gets a unique code, and there's a few non-printable control characters below 0x20, which is the space, and 0x7f is also just like a delete character. And you can get a nice table of them from ASCIItable.com, or just if you have a Linux machine, then man5ASCII will bring up the ASCII table. If you're interested in what it looks like, here it is in decimal, and here it is in hex. Then base 64 is an extremely useful encoding scheme, because any binary data can now be represented as printable text. It uses characters capital A through Z, lowercase a through Z, 0 through 9, and then plus and a slash typically used. You can have other characters there, but slash is the most standard. And then what base 64 does is it treats a stream of 8-bit bytes. It'll take them 6 bits at a time, and then each 6 bit it'll encode into 1 character, which means, well, since normal ASCII is 8 bits, it's going to be slightly larger than the original text. And since it's 6 bits at a time, it's not going to necessarily be a nice multiple of 8, so you'll see an equal sign at the end that's used for padding to make it a nice multiple of 8 bits. Then, for example, base 64 represented in base 64 is, well, that. And if you're on a Unix machine, then you have a command called base 64, which you can then use to encode and decode base 64. So let's see. For example, here I have just, can you see that? Is that too small? That's probably too small. Can you in the back see it? Or should I make it bigger? A little bit more? That's probably better. So like here I just have some data, which if you look at it, it's encoded in base 64. I'm not going to go through all of it, but trust me, that's just ASCII text. Actually, don't even have to trust me. It says that it's ASCII text. But if we go base 64, decode that data.bin, then if you look at that, then It's a PNG, which you can see right there. It's a nice stock image, but it's extremely useful if you need to send data across any kind of network or something where you don't want to risk normal binary data being corrupted in transit, but it'll send like normal text just fine. It used to be important in email, but it's gotten a bit less important because email standards have changed a bit. But then the next part is substitution ciphers. Basically, these just replace one value with another value. And there's a couple types. Monoalphabetic ciphers. Basically, you have like a single thing that you replace it with. Common examples. Morse code is probably the most widely used substitution cipher. Then Caesar cipher is a popular one that's used for teaching what substitution ciphers are, and then the shift ciphers are related to that, but they're generalized form. Then you have polyalphabetic ciphers, which you don't have just a single one-to-one relationship. You can have, depending on how the cipher algorithm is set up, you can have multiple different things depending on the key. And a great site that has a lot of nice tools that let you play around with this is decode.fr. Let's see if I actually go there. We can close that. Well, I guess there if someone missed the sign-in sheet. Let's see. Oh no, it's gonna be in French. English. Let's see. Did you get it?
Yeah.
All right. But here you can see they have a nice list of just normal like ciphers, and then there's all sorts of stuff here. Data processing, you can do text, image stuff. But I'm sure most people probably know what Morse code is. It takes, you get some text, then you turn it into a series of short and long tones, represented as generally as a dot for the short tone or a dit, and a dash for the long tone or a da. And then sometimes words are separated by a slash when it's written down just for extra clarity, but it's not going to be encoded. There's no slash in between there if like you're listening to Morse code from somewhere. Morse code is based off the frequency of English letters because the person who made it, I guess, knew English the best. And since it's based on the frequency, then different characters have different length. Here you can kind of see that where here's Morse code, and then the same in Morse code where M is just da da, and then O is da da da. So those are already slightly different lengths. And here is the table. You can see that E is just a single dit, and then T is just a single da. And those are the most common letters in the English language, compared to something like J or Q or Y, which are four marks long. And then numbers are, I guess, kind of counting up in some sense. But a Caesar cipher is basically just each letter is just shifted over 3 spaces. So an A becomes a D, a B becomes a E, and so on. And then once it hits the end of the alphabet, it'll wrap around. So you have Z is C, Y will be A, B, and so on. So if you have the word secret, and then that would be VHF UHW when it's encoded with a Caesar cipher. Shift cipher is just the generalized form of a Caesar cipher, where each letter is shifted left or right by some fixed amount, which is predetermined. And if you have some shift of n, then you can do the same thing with the shift of 26 minus n in the opposite direction, because 26 is how many letters there are and it wraps around. So then secret, if you shift it over 10, would be COMBOD. The problem with shift ciphers is it's vulnerable to frequency analysis because each letter becomes a different letter, but it becomes the same different letter each time. So kind of like if you go back to the Morse code, you can see kind of which letters are the most frequent. For example, E. And then here you can see that O is the most frequent letter in here, so you can make a decent guess that it's probably going to be E or some other common letter, and it corresponds to the 2 E's here. Vigenere cipher is a polyalphabetic cipher because it's basically like multiple different shift ciphers, but they're just chained together in a sense, where you have a key which is some word, and you use that each letter of the key to basically encode a shift amount based on where the letter is in the alphabet. And then if the key is shorter than the text you're trying to encrypt, then you're just going to repeat the key over and over. For example, secret, if you use the key word, then you get OSTUAH. Then here you can see that the 2 E's don't line up anymore. There's no 2 of the same letters here, so it's less vulnerable to frequency analysis as a result. Here you can see kind of how it works, where if you have some letter, let's say S, and then the key has a W there, so you'd go down to W, and then you'd end up here at O, which you can see there. You can do basically the same thing in reverse as well. But here you can see that the first row is basically the same. It corresponds to a shift of 0, and then each corresponding row, it shifts over 1 from the previous one. That is basically modular arithmetic, but with letters. And modular arithmetic is basically a system where integers will wrap around a specific point, which is called the modulus. And most people are probably familiar with modular arithmetic, even if they don't know it. For example, if you just look at the hands of a clock, it wraps around at 12. So for example, 13 in 24-hour time is 1 in 12-hour time, because it wraps around past the 12 and it gets to 1. Then you can also think of it as just the remainder portion of when you're dividing a number. So for example, here's the same example. 1 is 1 when you divide it by 12, specifically using integer division, where 1 divided by 12 is 0, and then you have a remainder of 1. And then 13 divided by 12 is 1, and then you have the remainder of 1. And then most normal arithmetic rules work in modular arithmetic as well. For example, if we assume that A is congruent to B mod n, then A plus K is also congruent to b plus k, because if a and b are the same, then you're adding the same amount to both, it's still going to be the same. Similarly for multiplication, because, well, that's just, multiplication is just multiple additions back to back. And then XOR is a common operation, but it's basically equivalent to addition mod 2, where here you can see basically x and y, and then if you take the XOR, then you get 0, 1, 1, 0. And then if you look at here, if you add the two in binary, it would be 0, 1, 1, and then 1, 0. But if you discard the carry bit, so then you get the same thing as the normal truth table. So that way, since 1 plus 1 would be 2, then it's 0, because 2 divided by 2 is 0 with then no remainder, or 1 with no remainder. And then XOR can be used basically for a one-time pad. One-time pad is the only classical encryption scheme that provides perfect secrecy, where basically it means that if you have some ciphertext, then without the key it's impossible to get the plaintext out of it. And one-time pad is just simple modular arithmetic, where if you encrypt something, you just add the key onto the message, and then to decrypt it, you just add the key onto the ciphertext. And if you remember, XOR was basically addition, so XOR can be used to create a one-time pad. And a one-time pad can't be cracked if the key is truly random, because if you add a random number onto any other number, well, the result is also another random number. And then it can also, part of the stipulation is that the key length has to be the same as the message length, because if it's not, then you'll start getting repeats, and then that's no longer quite as secure. And then you have to make sure that the key is never reused, because if someone finds like an old code book with keys, they can start trying to use those, and if you reuse a key from there, then they can decrypt your text. So if you use it once, then discard the key. And then similarly, obviously it has to be kept secret, because if you don't keep the key secret, then anyone can decrypt your data. But you can probably see that it's inconvenient, because if you want to use the one-time pad for something, you will need twice the space of the plaintext, because if the key is the same length, like you see here, then if you have some, I don't know, some letter that you want to encrypt, well, basically you'll need a duplicate of that, but that's used as the key. And then you'll have to securely exchange and store the keys if you want to maintain the integrity of it, because if someone can eavesdrop on your key, then, well, it's useless again. Here you can see where if you have some plaintext such as the word pizzas, and then you have this key here in hex, and then if you do an XOR on the ASCII value of each character in the word pizzas with corresponding to 1 byte in the key, then this is the ciphertext you end up with. And if you try to brute force the key, in this case, you'll come across 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and if you XOR them together, you'll get this, and you might think that's correct because you get something sensible as the plaintext, in this case the word secret, and obviously if you see the word secret somewhere, then you must have found something, but in this case, you didn't find anything because the real plaintext was pizzas. And because XOR is a really convenient way of doing the addition, it's sometimes called just the XOR cipher or XOR encryption. And let's see if I can see if I can actually do that on the fly. Let's see. I have a plain text. What was that? Pizzas. And let's see. If we get should hopefully give us. That looks correct, I think. And then, what's the key? X1, 1, 2, 2. Hope I got it right. Let's see if I actually got this. 1, 8. Yeah. All right. So then, let's see if we go. Ciphertext would just be. Would that be P XOR C for P and C in. See, 6, 6. Right. So then, let's see, where's the. If we have the second key, which is not the correct one, that would be 1, 1, 2, 2, 3. Then, let's see. If we try to do the same XOR there, let's see. Let's see, call this plaintext 2. Should be the same. Hopefully. No, it's not. Of course. That looks more correct. Let's see if I just then. You can see the word secret, which if you didn't want to trust me on just the text here, then you can see that brute forcing the key would most definitely result in the wrong decryption. And let's see, where was that? See if I can, there's some neat stuff here if I can find. Let's see, Caesars. Let's see. Enter. Will it work? No, it won't. Let's see if it'll load. All right. So for example, you can do stuff like, if you just perform a Caesar cipher on it, you'll get this. Let's see if I can. And then let's say you have this text and then you don't know what it is. Well, this site will just try every single thing, and then based on that, as it loads, then it has them sorted here based on like what it thinks is most likely. But in this case, it's down here, it's secret text. But basically, this site is going to sort them based on what looks the most, I guess, like a word. But, well, these don't really look like words to me, but they have a bunch of other stuff here. Like, let's see, if we go to the Vigenere Cipher, I think they have it here somewhere. Let's just look for it. There we go. Let's see, where was the, go back here, secret word. See once it loads. It should hopefully give us the same answer. Does that look the same? Yeah. Oh, what this site does is, for example, if you don't know what the key was, and then it'll analyze it for you, and then it'll hopefully find something. Question is, will it? I guess not. Here it's just trying all kinds of stuff. none of those seem very correct. But then, if you know part of the key, for example, in this case, let's see. Then here, they'll basically just try different combinations, and then it's apparently not going to find it. That's disappointing. Let's try again. Let's see if it gives a different result. Well, now it got it, obviously. Interesting. But like you can see, the Vigenere cipher it's a bit stronger than just the plain Caesar cipher, but there are ways to do it. I guess this site's not very good at it. Let's see. There's some other interesting ones. Let's see, what are some interesting ones? Rail fence cipher is an interesting one. Let's see. Let's see if it shows the actual like picture for it. Let's do it. Basically, what rail fence does is you'll read the text basically in a diagonal, and then yeah, here we go. We get TEXTEXT. Basically, in this case, you only have 3 rows, so then you go in a diagonal like this, and then you just read across. You get TTETETSX as the ciphertext, which it's not very secure because it still keeps the same text, the same letters, and it's not too difficult, the plain rail fence cipher, to just crack by just trying different heights. Yeah. Is there any questions here? Do you have any questions about anything? Next week we're gonna go over like RSA and some other stuff like that. Do you have any questions for today? I went actually faster than I expected. Oops. Alright, well, let's see. I have the... Is there anything else? Is there anything particular that you'd like to see next week? Nothing in particular? Alright, because I was just wondering. What? Alright. I guess I'll have to surprise you. I don't know. Will I? That's a good question. There's everyone's favorite OBS screen. Alright, let's see.